So good morning dear, welcome back. So in the last lecture we discussed very important algorithm, that is gradient algorithm, background of that algorithm, that how the operation rule works and how the parameters initializations are done, all kind of things we discussed. Now in a more formal way, today we are going to discuss three algorithms based on the principle which we have studied. First one is known as batch gradient algorithm. So the algorithm works like this. This Wj is a parameter attached with the jth feature is assigned to Wj. This is the operation rule which we have deduced last class, and this is your actually that derivative. So this minus alpha divided by n, n is for convenience, because we are talking about 1 to n. N is the number of samples. In your housing price of Windsor city, I think there are some 350 entries around that. Okay, so those are the samples, and this is the I equals 1 to n. Out of 350, what will be the m? Okay, so normally, as I told you, that you may consider taking some 250 for training purpose and rest for testing or validation purpose. Now, this batch which you are taking for training is being utilized for the algorithm. Okay, so I equals to 1 to m is the training number of training samples. This is what the operation is going on, and suppose there are n number of features, so I need to simultaneously update Wj for j equal to 0, 1, 2, 3, 0. 0 means the first term, the bias term. Okay, so simultaneously we have to update these parameters. This is how the algorithm works. Now this is fine when sample number is, as I told you, that 200, 250, even 1000, even 5000, that's fine. Today's computers are there. So as you can see, algorithms, how it is working for taking a state, that is assigning a new value. It is fast evaluating, scanning through all the samples. Okay, I equal to 1 to m. Then alpha is a learning rate, will be multiplied divided by this to simplify a little bit. Then that term will be eliminated or deducted from Wj, and then Wj will take a new value. So as I say, this may be okay for up to 1000, several thousand, but for million, 4 million, 40 million kind of number of samples, this is a bit troublesome algorithm, right? And a practical example you can take that when the GDP calculation of India is taking place, that means we have 1.3 billion people, a little more than that. Okay, so 70% of that sample is quite huge one, right? So that is a little bit problematic, but otherwise this performs pretty good, you know. You see, now if I try to draw, for visualization we only can do that, okay. We have taken two parameters and we are doing contour plot, say. To see how the algorithm will work. Okay? And if you take learning rate, this is actually bowl second. Say W0, W1, and this is our JW, isn't it? And this is what? So this is where I want to reach, my algorithm want to reach, and at several sections we have cut this bowl and then projected it, showing it on this plane. Okay, this is what. So what is this? Suppose this is the point. Now, if you select alpha very small, then what is going to happen? Actually, you are selecting very small step, and that will be visualized here with large number of contour. So this is the contour plot. Okay. Okay. Large, small, very small alpha means large number of states will be required to reach here. So computationally, this algorithm will be poor, means it will require computation. If together with large n, very small alpha you select, then it will move. Say for example, this is initial stage, every state, these are these states, and this is the destination or goal. Okay, it reached. Okay, so these are the states. That means trickling down, here, there, it is reaching what here. So that's a problematic thing. Otherwise, this is very steadily it will actually move towards the optimum point. Okay. If your computation can actually permit for those examples, please use batch gradient descent algorithm. So the batch term is coming from there. I don't know, it could have been a group term also. Batch means the number of training set which you have taken. And you see, simultaneously the algorithm is working like this, updating this, and simultaneously you are updating j equals 0 to 1 2. So these are the parameters. Okay. So at the end you will get all the parameters when they converge, means there is no appreciable change in W0, there is no appreciable change in W1, W2 up to Wn. Then you stop the algorithm and you select those values of the parameter. That's how it works. So that's good, but how about this million and billion? Today in the big data era, you could have samples which are very big. Then batch gradient descent is not a suitable one. Why? Because I explained, for making one step further, it will first scan through all the samples. Okay. We want to avoid that somehow. Okay. So specifically for this reading, another modification we did, and the name of the algorithm is called Stochastic Gradient Descent Algorithm. Stochastic Gradient Descent Algorithm, SGD, which is very popular. What differently we do here? We just randomly support training samples. Same number of training samples you have, 250 odd samples. Okay. you shuffle them randomly and then run this loop for this training samples in Wj assigned Wj minus alpha times. This is your okay. So here you can see there is no summation sign, right? That means for every sample it takes a decision. Okay, it makes a state. So essentially it is faster than. So that is the basic difference you must observe. And for every j equals to that is every parameter, you need to run this inner loop, and then you upgrade, go to the next sample, and then again do this, go to the next sample, and that's how stochastic gradient descent works. Now let us try to see how it will look like in the contour plot. Okay. So again, let us take this example. Say I will not draw it because it is already drawn here. I will only do the contour plot. Okay. If here is your goal point, those are the states, right? So what you have done randomly, you have sampled the training sample. So it may happen that training sample is here, okay, and then it will somewhere else, then somewhere else. So in a very zigzag fashion, it may reach nearer to the goal point, and it may not reach to the goal point as precisely as batch gradient descent algorithm. But well, fine, if instead of reaching here, what is the harm? If my problem permits that I reach somewhere in the vicinity of the minimum point, sometimes that is okay, because the step length is so small, almost you reach there. But the advantage you see, quite faster, because you are always making a mistake. And the example could be in the, again, housing price in Canadian city. Whimsically, any house you select. What is this? Any house price you try to determine based on that house, floor area, number of rooms, number of story. That could be an example, right? Instead of taking one by one all the houses, right? Whimsically one house, you try to see parameters are converging, then okay, then move to another random samples, training samples, right? And that's the way, that's why it is called stochastic gradient descent. This random suppling of the training sample is very, very important here, okay, which is making a difference. So you can see the difference between these two contour plot here, or if say I will draw this also. Steadily it was making a state. Okay. So this is your batch gradient descent algorithm. This is stochastic gradient descent algorithm. This is very, very popular because really it can accommodate very large data set which you may have to process, and you may have large number of you may have large number of parameters. Okay. So everything is coupled with large, right? If large is not there, then you will use what? The algorithm which we have already. Right? You will use this normal equation. This is level and these are the features, and you know the features, and then W is done. But when really features are large, go and check whether Lecture gradient works for you, because its convergence is precise. Then go and see if that is number of samples used. Switch over here, stochastic gradient descent. Okay, here you are compromising a little bit about the precision, but that's unavoidable. Okay. So you can see the advantage and disadvantage of both the algorithms. What if we could design another algorithm which will take best of both the algorithms? That is precisely done, and the name of the algorithm is MiniBatch gradient descent algorithm. MiniBatch gradient descent algorithm. The term mini is significant here. So instead of randomly sampling a training sample, what we are doing? Randomly shuffling a batch. Say I decide it should be some 100 or 1,000 sample will consist a batch. Again, it is your decision. Whether it will be 1,000 or 10 or 100 or more than that. Okay, 10,000 maybe. Okay. So it depends on your problem. But if we can do that, means we are talking about a shuffling of not the individual sample but a batch. A shuffle the batch. And then within each batch, you see, this is my updating rule. Repeat for I equals to m is the number of sample. Run the loop, wj assigned value equals to wj minus alpha, summation of I equal to 1 to b divided by times, this is mine as earlier. Okay, so this is the term, and this requires only one step. It will take one step only as you have decided the batch size. It will calculate all the samples within that batch, and then it will make a step. Difference is clear. Here it was waiting for all the samples. Here the algorithm was waiting for all the samples, whatever you have, a million samples, before taking a step, before updating this parameter. Okay? Here, on the contrary, sampling, whimsically it was taking a sample and taking a step. Okay, again, sampling and taking another randomly selected sample, taking a step. That's how we try to reach to the optimum point. And this to merge together, what we did here is that batch, mini batch we call it. That mini is in your hand. It could be 10, 100, 1,000. Okay, 10,000 depending on your problem and the computation you can afford. And then this is exactly similar to batch, but mini term is here. So if you do the contour plot, it has been observed that contour plot will be like this only. Okay, in between contour plot is important, what you can do. in a much more, much more stable way than stochastic gradient descent. It will reach you or algorithm to the optimum value. Okay, so that is MiniBatch gradient descent algorithm, stochastic gradient descent algorithm, and the story of batch gradient descent algorithm. And it turns out to be that if you can appropriately vectorize this MiniBatch gradient descent algorithm, sometimes it will perform much better than even stochastic gradient descent algorithm. Okay, so that's an advantage, but we need to vectorize this properly because batch size is there. Okay, so if you put your little red, then that's the story I have to say. So out of this algorithm, again, you are in the driving seat. You will have to analyze the problem, which one you should select. Okay. Now, L is large, so you left the domain of normal equation. You entered here. Again, you have to analyze. I have several options: batch, stochastic gradient descent, MiniBatch gradient descent. Which one I should opt? That will again depend on you, depend on the problem and the analysis power which you are acquiring through learning. So that's all I wanted to say. Okay, so these are the three algorithms. So and we'll solve some problems now. We are capable of solving problems related to this, and I suggest that from fundamental, without taking the function of Python, you will code and learn on maybe housing price of Windsor City of Canada. Okay, you can do that. Till then, stay safe. Bye bye.